close your eyes and let's go somewhere very far away. Somewhere past the moon, past the sun, past every star you have ever picked out of a clear night sky. Let's go out to the edges of galaxies, where something strange and quiet is happening in the dark. At the center of many galaxies, there sits a supermassive black hole. It is a place where gravity has folded space so tightly that nothing, not even light, can climb back out once it gets too close. You would think a thing like that would only pull things in. You would think it could only take, never give. But some of these black holes do something else entirely. They fling narrow beams of matter out into space at speeds close to the speed of light itself. These beams are called jets. They can stretch for thousands of light years, far longer than the galaxy that made them. Picture a single beam of light, so long it could stretch past 100,000 suns, lined up end to end, moving so fast that it seems to bend the rules of the universe. And here is the strange part. After decades of watching, of building bigger telescopes, and waiting patient years for answers, we still do not fully understand how a black hole does this. That is the heart of tonight's mystery. How does an object defined by pulling everything toward it manage to launch matter away from it at almost the speed of light? And why do some black holes do this loudly, while others, just as massive, stay completely silent? One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Let's keep looking out into the dark. Some of these jets have been traveling for so long that the light we see tonight left its source before the Earth had oceans. They cross entire galaxy clusters, plowing through thin gas that drifts between galaxies, leaving behind glowing structures that radio telescopes can still detect today. Some of these structures are so old and so large that they stretch across a distance greater than 10 Milky Way galaxies placed side by side. Astronomers first noticed something odd about these distant points of light back in the 1950s and 1960s. They looked like stars through a telescope, but they gave off far too much energy to be ordinary stars. People called them quasi-stellar objects, which eventually became the word we use now, quasars. It took years of careful work to realize that a quasar is not a star at all. It is the bright, energetic center of a galaxy, powered by a supermassive black hole feeding on gas and dust. That discovery changed how we understood galaxies. It also opened a much bigger question that we are still trying to answer tonight. Because feeding on gas does not fully explain the jet. Falling matter should simply fall in and disappear past the black hole's edge, the event horizon, the boundary past which nothing escapes. Instead, some small fraction of that matter gets redirected. It gets funneled, sped up, and thrown outward in two narrow beams, one from each pole of the black hole, like some vast cosmic lighthouse turned inside out. Some researchers think the answer lies in the magnetic fields twisted around the black hole, fields that may act like invisible slingshots. Others focus on the black hole's own spin, wondering if a rotating black hole can somehow lend its spin energy to nearby matter, flinging it outward instead of pulling it in. Both ideas are still being tested. Neither one fully closes the case. For tonight, we do not need to solve it. We only need to sit with the wonder of it. Somewhere out there, right now, a beam of matter is racing across the space between galaxies, glowing faintly in wavelengths our eyes cannot see, carrying energy from an event we still cannot fully explain. It has been traveling longer than human history. It will keep traveling long after we are gone. Think of the black hole not as a hungry mouth, but as a dark, quiet engine, one that somehow turns falling matter into a beam of light thousands of light years long. We know some of the pieces. We do not yet know how they all fit together. And that gap between what we have measured and what we understand is where tonight's story lives. Let yourself rest inside that gap for a while. There is no need to reach the answer tonight. There is only the shape of the question, vast and dark and strangely beautiful, stretching out across the sky like the jets themselves. Let's picture one of these jets, plainly, the way you might see it in a photograph taken by a radio telescope. Imagine a beam of light, thin and straight, stretching out from the middle of a galaxy. It does not curve, it does not waver, it shoots outward like a line drawn with a very steady hand. Some of these beams reach out for thousands of light years. A single light year is the distance light travels in 1 full year, moving at the fastest speed anything can move. So a jet that stretches 10,000 light years is a beam that light itself would need 10,000 years to cross, end to end. Now, compare that to something familiar. Our own galaxy, the Milky Way, is about 100,000 light years across. Some jets from black holes reach lengths that are a meaningful fraction of that entire galaxy's width. A few rare jets stretch even further, spanning millions of light years, longer than the galaxy that made them by a factor of 10 or more. Try to hold that in your mind for a moment. A structure launched from one tiny point can grow larger than the whole star-filled home that built it. And here is the strange part. The point where this beam begins is impossibly small by comparison. It starts near a supermassive black hole, an object with a mass millions or even billions of times greater than our Sun, packed into a space that might fit inside our solar system. From that tiny, dark origin, matter is somehow thrown outward, across distances that dwarf entire galaxies. The size difference between the source and the beam is almost impossible to picture. It is like a single grain of sand, somehow launching a line of light that stretches across an entire country. What is actually inside this beam? Mostly, it is plasma, a hot, electrically charged gas made of particles stripped of their outer structure. These particles move at speeds close to the speed of light itself, which is why scientists call this kind of motion relativistic, a term that simply means the object is moving fast enough that the strange rules of Einstein's relativity start to matter. At these speeds, time and distance stop behaving the way they do in ordinary life. A jet moving close to light speed can appear to do things that seem to break the ordinary rules of motion, and we will look closer at that puzzle later in this program. From Earth, we cannot see this plasma with our eyes. It glows in radio waves, a form of light far outside what our eyes can detect. Radio telescopes, some of them scattered across different continents and linked together, are what first revealed these jets as glowing lines instead of blurry smudges. Without those instruments, this entire structure would remain invisible, hidden in a part of the light spectrum humans cannot naturally sense. The scale in time is just as hard to hold on to as the scale in space. Some of these jets have been observed for decades, and in that time, they have hardly changed shape at all. That stillness is deceptive. It tells us that whatever process builds and feeds a jet must be steady over stretches of time far longer than a single human life, maybe over millions of years. One idea is that a black hole can power a jet for as long as it steadily pulls in matter from its surroundings. A competing idea suggests the process might switch on and off, in cycles, glowing brightly, fading, and returning later in the galaxy's long history. Which of these patterns is closer to the truth is still an open question, and the answer may differ from galaxy to galaxy. So, when you picture one of these jets, picture something both enormous and strangely delicate, a line of glowing plasma, thinner than the galaxy around it, reaching out over distances that make our entire solar system look like a single dot. Picture it moving at speeds so close to light that it seems to bend the rules we use for everyday things. And picture it doing all of this quietly, invisible to human eyes, detected only through instruments built to listen to a kind of light we cannot naturally see. That is the shape of the mystery in its simplest form. A tiny dark source, an impossibly long beam, a process steady enough to last for ages, yet still not fully explained. We know what the jet looks like from far away. We are still trying to understand exactly how it begins. Before a jet can ever leave a black hole, something quieter has to happen first. Gas and dust must gather, slow down, and spiral inward. This slow gathering forms a flat, glowing ring called an accretion disk, and it may be the true starting point of the whole story. Picture a wide, thin ring of hot matter circling a dark center, glowing orange and white, like a coal that never cools. That ring is patient. It can wait for a long time before anything dramatic happens at all. The matter in that disk does not fall straight in. Instead, it drifts inward, slowly rubbing against itself, losing energy bit by bit. This friction heats the gas to millions of degrees, and the disk begins to shine with its own light, sometimes bright enough to outshine every star in its galaxy combined. That brightness was one of the first clues that led astronomers, back in the middle of the last century, to realize something strange was hiding at the center of certain galaxies. Those bright centers came to be called quasars, a short name for what was once called a quasi-stellar radio source. At first, they looked like ordinary points of light, almost like stars, but their light changed too quickly, and their distances were too vast for them to be stars at all. Slowly, researchers pieced together a startling idea. These were not stars. They were entire galaxies, with supermassive black holes at their hearts, feeding on surrounding gas through disks like the one we are picturing now. The disk itself seems almost gentle compared to what may come next. Matter swirls, glows, and slowly falls inward, pulled by gravity toward the black hole's event horizon, the invisible edge past which nothing can return. Most of the material never makes a jet at all. It simply falls in, or it drifts away as a slower wind, blown outward by heat and pressure. The jet, if one forms, is something else. It is a much smaller fraction of the material, launched outward instead of inward, moving at speeds close to the speed of light. Exactly how the disk hands off its energy to build a jet remains an open question, and it is one that connects gently to the ideas we will sit with soon. One long-standing idea is that the disk's inner region twists magnetic fields into tight, powerful shapes, and those fields somehow grab hold of a small amount of matter and fling it away from the black hole entirely. Another idea suggests the spin of the black hole itself, not the disk, provides the real push, with the disk acting more like fuel than like an engine. Both ideas agree on one thing: the process takes conditions that must be delicate and specific. The black hole needs enough gas nearby to build a disk in the first place, and that gas has to arrive in a way that keeps the disk stable rather than chaotic. Too little gas, and there is nothing to accelerate. Too much gas falling in too fast, some researchers suggest, might overwhelm the very structures needed to launch a clean, narrow jet. The balance seems fragile, and we still do not fully understand where that balance point lies. Time plays its own quiet role here. A disk may take thousands of years to fully form and settle into a stable shape, slowly organizing its motion into smooth, circular flow. During that time, the black hole simply waits, growing heavier as matter trickles in its gravity strengthening bit by bit. Nothing about this process happens quickly. There is no single dramatic moment when a jet switches on. Instead, there seems to be a long, slow build, hidden from any observer who might wish to watch it happen in real time. We know the disk exists because we can see its glow, and we know jets exist because we can see their long streams of light reaching across space. What we cannot yet see clearly is the exact moment where one becomes the other, wherein falling matter turns into outgoing light. That transition happens far too close to the black hole for our current telescopes to resolve, hidden within a region smaller than the solar system, sitting near the edge of the event horizon itself. So the disk remains, for now, a quiet mystery wrapped inside a louder one. It feeds a sleeping giant that may, under just the right conditions, wake into something that reaches across an entire galaxy. Whether every disk eventually leads to a jet, or whether most simply fade without ever launching one, is a question that stays open tonight, drifting unanswered above us like the light of the disks themselves, still traveling toward us from a very long time ago. Let's rest for a moment on a strange idea. Space itself can spin around a black hole. This is not just a figure of speech. A black hole's rotation drags the space near it around in circles, like a spoon stirring thick honey. Physicists call this frame dragging. It means that close to the black hole, even empty space is forced to move. Nothing solid needs to touch the black hole for this to happen. The spin is written into the shape of space and time themselves. This detail matters because one of the leading ideas about jets says the spin of the black hole may be the true source of their power. The idea is called the Blandford-Znayak mechanism, named for the two physicists who worked out the mathematics in 1977. Their proposal is elegant and a little dizzying to picture. They suggested that a spinning black hole, threaded by magnetic field lines from the swirling disk around it, can act like a kind of cosmic dynamo. The black hole's rotation twists those magnetic field lines into a tight spiral. That twisting can pull rotational energy out of the black hole itself and pour it into the particles nearby, flinging some of them outward at nearly the speed of light. It is worth sitting with how strange this is. The energy for the jet in this picture comes not from matter falling in, but from the black hole's own spin slowly winding down. The black hole becomes something like a battery. Its rotation is the stored charge. The magnetic field is the wire, and the jet is the current flowing out into the dark. Where do these magnetic field lines come from in the first place? They likely start in the disk of gas and dust that spirals around the black hole, the same feeding disk we described a moment ago. As charged particles swirl through that disk, they naturally generate magnetic fields, in much the same way a coil of wire generates a field when current runs through it. Some of these field lines get dragged inward and anchored near the black hole's edge, close enough to feel the full force of its spin. It is a delicate arrangement. The disk supplies the field. The black hole supplies the twist. Together, they may build an engine unlike anything found on Earth. Not every researcher agrees this is the whole story. Some prefer a different, though related picture called the Blandford-Payne mechanism. In this version, the jet's power comes mostly from the spinning disk itself, not from the black hole's rotation. The disk's own magnetic field lines, anchored in the whirling gas, could fling material outward the way a rotating garden sprinkler flings water. Under this idea, a black hole would not even need to be spinning especially fast to launch a jet. The two mechanisms are not necessarily rivals. Many researchers suspect both processes might work together, with the black hole's spin providing an extra boost on top of the disk's own contribution. Untangling how much each one contributes remains an open question, and one of the reasons is that we cannot yet see the region close enough to the black hole to watch the process directly. There is something worth noticing in how patient this whole idea is. A black hole's spin, once given to it, does not need to be renewed constantly. It can act like a reservoir, slowly drained over millions of years, powering a jet long after any single meal of gas has been swallowed. This might help explain why some jets seem to keep going steadily, even when the flow of new material into the disk rises and falls. The spin becomes a kind of memory, holding onto energy from events that happened long before the light we see tonight ever left its source. None of this has been confirmed by direct observation of the region right at the black hole's edge, called the event horizon, the boundary past which nothing, not even light, can return. The magnetic fields, the twisting, the drag of space itself, all of this is inferred from mathematics and from the behavior of jets we observe from very far away. Some scientists wonder whether an entirely different process, still undiscovered, might be doing some of the work instead. It is one of the appealing puzzles of this whole picture. A black hole, an object defined by what it swallows and hides, might also be the quiet architect of something that races outward for 100,000 light years or more. Whether the credit belongs mostly to the spin of the hole, the churn of the disk, or some partnership between the two, remains something astronomers are still working out patiently, one observation at a time. The way you might slowly piece together the shape of something enormous, glimpsed only by its shadow. Picture a black hole wrapped in lines you cannot see. These are magnetic field lines, and they may be the true architects of the jet. No one has ever photographed one directly, but their fingerprints show up everywhere in the light that reaches us. Magnetic fields are strange things to imagine in space. There is no wire, no coil, no machine humming somewhere in the dark. The field grows out of the churning disk of gas that circles the black hole, the one we described a moment ago. As charged particles swirl through that disk, they drag magnetic lines with them, twisting them the way a spoon twists cream into coffee. Over time, these lines can grow taut and organized, stretching up and away from the disk like strings on some vast, invisible instrument. Here is where one of the most elegant ideas in modern astrophysics comes in. Some theorists propose that these magnetic lines become anchored to the spinning black hole itself, not just the disk around it. If that happens, the black hole's rotation can act like a motor, winding the field lines tighter and tighter, the way you might twist a rubber band around a stick. This twisting stores enormous energy, and when that energy releases, it may fling particles outward along the twisted lines, faster and faster, until they are moving at nearly the speed of light. This is the heart of the Blanford's magic idea we touched on before, though scientists still debate exactly how the energy makes its final leap from spinning space into racing particles. Gravity plays its part too, but not in the way you might expect. Close to the black hole, gravity is so extreme that it does not simply pull things in. It also seems to help organize the chaos, pinching the inner edge of the disk and creating sharp boundaries where hot gas and magnetic pressure meet. Some researchers think this boundary region, sometimes called the corona, might glow with its own light, made of superheated particles bouncing between tangled fields. Whether the corona feeds the jet or simply sits near it remains an open question with no easy answer yet. Radiation adds another layer of pressure to this scene. Photons, tiny packets of light, stream outward, from the white-hot disk in staggering numbers. Some scientists wonder if this radiation itself gives particles a small outward shove, adding just enough energy to help launch them past the point of no return. Others think the radiation pressure is far too weak on its own, and that magnetic forces do almost all of the work. Both camps agree the true balance of forces likely shifts from one black hole to another, and perhaps even from one moment to the next within the same system. Then there is the odd behavior of the space near the event horizon, the boundary past which nothing escapes. General relativity tells us that a spinning black hole drags space and time along with it, like a spoon dragging syrup around its rim. This effect, called frame dragging, may help twist magnetic lines even harder than the disk alone could manage. It is a strange, almost dizzying idea. The fabric of space itself, moving and carrying magnetic order out into the emptiness above the black hole. All of these forces, gravity, magnetism, radiation, the twisting of space, seem to work together, but nobody has built a complete picture of how they combine. Some computer models can produce jet-like structures using only magnetic fields and spin. Other models need extra ingredients, like turbulence in the disk or sudden bursts of infalling gas, to get a jet moving convincingly. Each model captures a piece of the story, but none of them has been confirmed by a direct, close-up view of the region where the jet actually begins. It helps to think of these forces the way you might think of wind shaping a sand dune, slow and patient, working over long stretches of time. Except here, the dune is made of plasma, the wind is magnetism, and the shaping happens near the edge of a black hole rather than a desert. The particles that emerge from this shaping travel for thousands of years before they ever reach us as light or radio waves, carrying the memory of forces we still cannot fully explain. So the picture that scientists are piecing together is one of quiet, immense tension, magnetic lines wound tight, gravity carving sharp edges, light pressing outward, space itself twisting near the black hole's spin. Together, these may be the invisible hands that guide raw matter into a beam that outshines its entire galaxy. But how those hands truly cooperate, and which one leads the motion, remains one of the open puzzles waiting patiently in the dark for someone to finally see it clearly. Let's think about scale for a moment. Not the scale of the jet itself, though that is vast enough. Let's think about something smaller and somehow harder to imagine. Let's think about a single particle, moving so fast that it carries the punch of a thrown baseball packed into a space smaller than an atom. These are called cosmic rays. Despite the name, they are not light. They are particles, mostly protons, stripped bare and flung across space at speeds close to the speed of light itself. Most cosmic rays are gentle by comparison, born in ordinary stellar explosions inside our own galaxy. But a small number of them arrive carrying an energy that makes physicists uneasy. These are called ultra-high-energy cosmic rays, and they are, particle for particle, the most energetic objects we have ever detected in nature. Picture a proton. It is smaller than anything you could ever hope to see, smaller than a grain of sand shrunk down past the point where the comparison even makes sense. Now imagine that single, near-invisible speck hitting the top of our atmosphere with as much energy as a fastball thrown by a professional pitcher. That is roughly what the most extreme cosmic rays carry. A speck of matter, doing the work of a swung bat, arriving after a trip that may have lasted millions of years. To make a particle move that fast, you need an accelerator on Earth. Our best particle accelerators are enormous machines, built in rings tunneled underground, some of them 17 miles around. use powerful magnets and careful engineering to push particles close to light speed, and even then, they fall short of the energies we see arriving from space. Whatever is producing the most extreme cosmic rays is doing something our best human engineering cannot yet match, and it is doing it somewhere out in the dark, without wires, without walls, without anyone tending the machine. This is where the black hole jets come back into the picture. One leading idea is that these jets, especially the ones blasting out of the centers of active galaxies, act as cosmic accelerators far larger and far more powerful than anything we could build. A jet can stretch for hundreds of thousands of light years. If you shrank our entire solar system down to the size of a coin, a single jet from one of these galaxies could still stretch the length of a football field, made of nothing but the coin-sized solar systems laid end to end. The particles inside that jet have room to run, and room to be pushed again and again by shifting magnetic fields, gaining speed the way a skater gains speed with each new push off the ice. But here is the trouble. Even with a jet that long, it is difficult to explain the very highest energy particles we detect. Some researchers wonder if it takes more than one push. Perhaps a particle gets accelerated near the black hole, then again farther out where the jet slabs into gas between galaxies, gaining a little more energy at each stage, like a ball bouncing down a set of stairs and picking up speed at each step. Others think the acceleration might happen in short, violent episodes, sudden turbulent knots within the jet where magnetic fields tangle and snap, releasing bursts of energy into nearby particles all at once. The honest difficulty is that we cannot trace a cosmic ray back to its source, the way you might trace a beam of light back to a flashlight. Magnetic fields scattered across the galaxy bend the path of charged particles, so by the time one of these protons reaches our detectors, it has been nudged and curved so many times that its trail leads nowhere in particular. It is a bit like trying to find where a single raindrop fell by looking only at the puddle it left behind, long after the storm has passed and the wind has stirred everything else into the water. So the sky keeps sending us these fast, tiny messengers, and we keep struggling to read their return address. Are they born deep inside the churning disks that feed supermassive black holes? Are they flung outward by the jets we have been picturing, accelerated over hundreds of thousands of light years? Or is there some other engine out there, one we have not yet imagined, quietly outperforming every collider we have ever built? The particles keep arriving. The question of exactly where and how they were made remains open, drifting along with them across the dark. Picture a flashlight shining somewhere out in the deep dark. Most of the time, you would see nothing at all. The beam would point away from you, sweeping past unseen. But every so often, a flashlight turns and its beam falls directly into your eyes. For a moment, that light seems far brighter than it should. This is close to what happens with a special class of galaxies called Blazars, and it may explain why some black holes appear to be the brightest objects in the whole sky. A blazar is not a different kind of object from the quasars and radio galaxies we have already met. It is the same jet of plasma moving near the speed of light, but seen from a very particular angle. When a jet happens to point almost directly at Earth, something strange happens to the light it carries. The light brightens far beyond what the jet's true power would suggest, and it flickers and changes over the course of days or even hours. Astronomers call this effect relativistic beaming. It happens because the particles in the jet are moving so close to the speed of light that the light they give off gets compressed forward, like water sprayed from a hose held by someone running toward you. The faster the motion, the tighter that spray becomes. When we happen to stand in its path, We catch far more of the jet's true brightness than an observer standing off to the side ever would. If you could hang in space and look at a blazar face on, what would you see? Not a beam so much as a point of light that refuses to sit still. It would flare and dim, sometimes doubling in brightness within a single day. Around it, the disk feeding the black hole would glow at the center, but the jet itself would likely outshine everything else. A needle of high-energy light pointed straight into your eyes. Some blazars shine so brightly across gamma rays, the most energetic form of light we know, that they rank among the most luminous steady sources in the universe. This brightening effect creates an odd problem for anyone trying to study jets honestly. Because a Blazars jet points at us, we get a magnified, exaggerated view of what is, in truth, a fairly narrow column of material. It is a little like judging the size of a whole forest by staring straight down the barrel of one tree's shadow. The Blazar view teaches us enormous amounts about the physics near the black hole, but it can also mislead us about how common or how powerful jets are across the wider population of galaxies. One theory holds that every galaxy with a strong jet would look like a blazar, if only we could rotate it to face us directly. In that view, blazars are not a special class of object at all, just an accident of geometry, a lucky alignment between an ordinary jet and an observer standing in exactly the right spot. Other researchers wonder whether blazars might also differ in some deeper way, perhaps in how their magnetic fields are organized, or in how steadily their black holes are fed. The debate over whether alignment explains everything or only part of the picture remains unresolved. The flickering itself carries its own mystery. Some blazars change brightness over years, tracking slow shifts in how much material falls towards the black hole. Others flare within minutes, which is strange because for a light source to brighten and dim that fast, the region producing the flare must be smaller than our solar system. Sitting near a black hole many light years across, what could cause such a small, sudden burst so close to the black hole's edge remains an open and active question, with several competing ideas about shocks, kinks, and tangled magnetic fields inside the jet. Because their jets point at us, blazars give scientists a rare kind of window. We can watch particles accelerate to nearly the speed of light, and then trace the light they produce almost in real time as it changes from one night to the next. Yet this same advantage is also a limit. We are looking down a very narrow tube, and most of what a jet actually looks like from any other angle remains hidden from view. So the blazar is both a gift and a puzzle. It hands us the brightest, closest look at the surface of a jet's fire, and at the same moment, it reminds us how much depends on where we happen to be standing in the dark. Somewhere out there, countless other jets are shining just as fiercely, aimed at points in space we will never occupy, their light forever missing us by the width of an angle we may never measure. On Earth, we have built machines to smash particles together at tremendous speeds. The largest of these, buried in a tunnel beneath the border of two countries, can push protons close to the speed of light. It took thousands of engineers and billions of dollars to build. And yet, somewhere out in the dark, a black hole does something similar without any effort at all. The particles inside a jet move at speeds our best machines struggle to match. Some carry energies millions of times higher than anything a human collider has ever produced. Cosmic rays, tiny fragments of atoms that rain down on our planet every day, sometimes arrive with energy so extreme that a single particle can strike with the force of a thrown baseball. That is a strange thing to picture. A single proton, smaller than we can imagine, hitting our atmosphere with the punch of something you could hold in your hand. Nobody knows for certain where these highest energy particles come from. Black hole jets are one of the leading suspects. The jet acts like a natural accelerator, far larger and far older than anything humans could build. Some researchers picture it as a slow funnel, one that gathers particles over thousands of years and gently pushes them faster and faster along magnetic field lines. Others imagine sudden bursts, moments when the jet becomes unstable and flings a batch of particles forward all at once, like a slingshot released without warning. The trouble is that these particles travel across such enormous distances that their original path gets bent and twisted along the way. Magnetic fields between galaxies, weak as they are, still nudge a charged particle off course over millions of light years. By the time a cosmic ray reaches Earth, it no longer points back toward its source. This is one of the central puzzles of the field. We can catch the particle. We cannot always say where it began its journey. One idea is that the particles gain most of their speed close to the black hole, in the tightly wound magnetic fields near the launching point of the jet. Another idea places the acceleration much farther out, in the shock waves that form where the jet slams into gas, drifting between galaxies. Both processes may happen at once, working together in ways we do not yet fully understand. The jet might act like a relay race, handing energy from one stage to the next, across unimaginable distances. There is also a question about what kind of particles are doing the accelerating. Some models suggest jets are made mostly of electrons, light and quick, buzzing along the magnetic field lines. Other models suggest protons carry much of the energy, heavier and capable of reaching the extreme levels seen in cosmic rays here on Earth. A jet could contain a mix of both, along with particles we have not yet detected. Each possibility changes how we imagine the inner workings of the jet, and each remains open. What makes this puzzle feel almost impossible is the scale involved. A jet can stretch for hundreds of thousands of light years, yet the particles moving fastest are smaller than an atom. We are trying to explain the tiniest objects in nature using structures larger than entire galaxies. It is a bit like trying to understand a single grain of sand by studying the shape of a mountain range. The connection is real, but the distance between the two scales is almost impossible to picture. Some scientists hope that future detectors, built to catch cosmic rays or the ghostly particles called neutrinos, might one day trace a clearer path back to a specific jet. If that happens, it would offer the first direct proof that black holes truly are the universe's most powerful accelerators. Until then, the evidence remains suggestive rather than certain. The pieces fit together in a way that feels convincing, but a piece or two may still be missing. Lying here in the dark, it can help to imagine one of these particles leaving its distant home. It slips out of a jet near a black hole, crosses vast stretches of near-empty space, and drifts through the quiet hum of the universe for millions of years. Eventually, it brushes against our atmosphere in the smallest possible way. We may never know its exact origin. We only know it came from somewhere far beyond anything we can see, carried by a process still waiting to be fully understood. Far from any galaxy that hosts one, a jet finally slows down. It has traveled for tens of thousands of years, moving at nearly the speed of light through the thin gas between galaxies. When it finally meets resistance, it does not crash. It spreads. Over time, it inflates a soft cloud of glowing plasma called a radio lobe, sometimes stretching wider than the galaxy that made it. Seen through a radio telescope, this cloud looks like a slow, silent explosion, one that has been unfolding for longer than human history. Radio galaxies get their name from this glow, which shines brightest in radio waves rather than visible light. Two lobes often bloom on opposite sides of the galaxy, fed by twin jets shooting out in mirrored directions. The whole structure can span more than 1,000,000 light-years, dwarfing the galaxy sitting quietly at its center. And yet the black hole responsible for all of it may be smaller across than our solar system. The scale gap between cause and effect is one of the strangest things about this whole process. What makes these systems feel cyclical is that they do not run continuously. Evidence from many radio galaxies suggests the central black hole can turn its jet on, let it run for a few million years, and then turn it off again. Some galaxies show faint outer lobes from an old phase of activity, sitting beside brighter inner lobes from a newer one. It looks almost like tree rings, layers of past eruptions preserved in glowing gas. Astronomers call these episodes duty cycles, borrowing a word from engineering to describe something that switches between active and quiet states. Why a black hole would pause and restart is still an open question. One idea points to the fuel supply. If the disk of gas spiraling toward the black hole runs thin, the jet may weaken or stop until fresh gas falls in, perhaps stirred up by a passing companion galaxy or a slow gravitational disturbance. Another idea points to instabilities in the jet itself, changes in magnetic field structure that could choke the flow of plasma for a while before it reorganizes and pushes outward again. Neither idea has been confirmed. Both remain reasonable guesses, sitting side by side. The timing of these cycles is hard to pin down because the timescales are so long. A jet that turns on for 3 million years and off for 1 million years would look, to a human observer, exactly the same in any single snapshot. We only see one frame of a very slow film, comparing many radio galaxies at different stages, almost like comparing photographs of trees at different ages, is currently the closest astronomers can get to reconstructing the full rhythm. These slow eruptions do more than just glow. The energy in a radio lobe can push against the surrounding gas, heating it and slowing its collapse into new stars. In large galaxy clusters, this heating may explain why the hot gas at the center does not cool down and form far more stars than observed. A puzzle sometimes called the cooling flow problem. The jet, still faint and expanding long after its violent birth, may be gently keeping an entire cluster of galaxies in balance. Whether this mechanism fully explains the missing cooling or only partly accounts for it is still debated among researchers who study galaxy clusters. There is something quietly humbling in picturing this cycle. A black hole, a few million times the mass of our Sun, launches a beam of plasma that outlives its own active phase by millions of years, drifting outward long after the engine that made it has gone quiet. The lobe does not know its source has paused. It continues to glow cool slowly and spread a fossil record of energy released long ago. In some systems, a second phase begins before the first lobe has faded, and the two generations of plasma sit near each other, like echoes from different decades. No one has watched a single radio galaxy complete a full cycle from start to finish, simply because a human lifetime is far too short. What we have instead is a gallery of snapshots, each one a different galaxy caught at a different point in its own private rhythm. Piecing together the pattern from these separate images is a bit like guessing the life story of a tree from a single cross-section of its rings. The rough shape of the cycle seems believable. The exact triggers, the exact durations, and the exact number of times a black hole might restart its jet across the age of the universe remain unresolved. Quiet questions drifting in the same dark that the jets themselves once crossed. Some jets fall quiet. The black hole that made them may have used up its fuel, or the disk of gas around it may have thinned to almost nothing. And yet the jet itself does not vanish right away. It lingers in the space around its galaxy, glowing faintly, long after the engine that built it has gone dark. This is one of the stranger neighborly relationships in the sky. A jet can outlive the very conditions that created it. Picture a radio galaxy that has been feeding its jets for millions of years. The plasma it has thrown outward has traveled so far that it now sits well beyond the visible edge of the galaxy, in lobes of glowing gas that stretch across hundreds of thousands of light years. If the black hole suddenly stopped launching new material, those old lobes would not simply switch off. They would keep drifting, keep glowing at radio wavelengths, slowly cooling over tens of millions of years. Astronomers sometimes catch these fading giants and call them relic radio galaxies, ghostly outlines of an engine that may no longer be running. This raises a quiet but important question. If the light we see from a jet's outer reaches left the black hole millions of years ago, are we watching a system that is still active, or one that has already gone silent, its final light still crossing space toward us? There is no way to know for certain just by looking at the glow. The jet's launch point, close to the black hole, can only be understood by watching for fresh, compact activity right at the center. Some galaxies show exactly that. Old, faded lobes far out, and a small, bright, freshly restarted jet near the core. These are called double radio galaxies, and they look almost like two sets of wings, one old and dim, one young and sharp, aligned along the same axis. What causes a jet to restart after going quiet is itself an open question. One idea points to fresh gas falling back toward the black hole, perhaps stirred loose by a passing companion galaxy or a slow gravitational disturbance in the surrounding gas. Another idea suggests the black hole's spin and magnetic field may cycle through periods of stronger and weaker alignment, turning the jet up and down like a dimmer switch over long stretches of time. Neither explanation is settled, and it is possible different galaxies restart their jets for different reasons entirely. The neighborhood around a jet matters just as much as the engine itself. A jet does not travel through empty space forever. It plows into the thin gas that fills the space between galaxies, called the intergalactic medium, and this collision slows the jet down, spreads it out, and eventually stalls it into the glowing lobes we just described. The density and temperature of that surrounding gas shapes how far a jet can travel before it loses its shape. A jet moving through a crowded galaxy cluster, thick with hot gas, may struggle to grow, while a jet in a quiet, sparse region can stretch on for staggering distances. This means the visible shape of a jet is really a conversation between two things: the black hole that launches it and the environment that receives it. Some researchers wonder whether this exchange helps explain a separate puzzle known as the cooling flow problem, in which the hot gas at the center of galaxy clusters should be cooling and collapsing far faster than it appears to be. A jet pushing energy outward into that gas, gently and repeatedly, might be part of what keeps the cluster from cooling too quickly. Whether this energy input is enough, and whether it happens consistently across different clusters, remains unresolved. There is something almost tender about the idea of a jet as a long echo, a structure that keeps existing in the space around a galaxy long after its source has quieted down. It suggests that a black hole's influence does not end at the edge of its accretion disk, or even at the edge of its host galaxy. It can stretch outward, fade slowly, and leave behind traces that outlast the very violence that made them. Whether every galaxy experiences this cycle of jets, turning on and off, whether it happens once or many times across a galaxy's life, and whether we can ever fully map how a jet's environment shapes its final form, are all still open questions. For now, when astronomers find one of these faded, ghostly lobes drifting far from any obvious source, They are looking at something like an old signal, still traveling through the dark, a quiet reminder that even the most powerful accelerators in the universe eventually rest. Somewhere out there, two black holes may sit side by side, each one just as massive as the other, each one feeding on gas at nearly the same rate. And yet, one of them throws a beam of light across half a galaxy, while the other stays dark and still. This is one of the quieter puzzles in the story of these accelerators. Mass does not seem to decide who roars and who stays silent. Astronomers call the loud ones radio loud, and the quiet ones radio quiet. The split is not gentle. A radio loud black hole can outshine its quiet twin in radio waves by a factor of 1,000 or more. Some researchers wonder if this gap means two different physical switches are at work, rather than one dial turned up or down. Others think it may be a matter of degree, not kind, with every black hole capable of producing a jet under the right conditions. Spin is one leading suspect. A black hole is not just a mass and a size. It also spins, and that spin twists the space around it in the leading theory for how jets are launched, called the Blandford-Znajek mechanism. Magnetic field lines anchored in the spinning space near the black hole act like the spokes of a slow, invisible wheel. Some researchers think a fast-spinning black hole can drive a much stronger jet than a slow one, simply because there is more rotational energy to tap. But measuring the spin of a distant black hole is difficult, and the data remain thin. The idea is elegant. It is not yet proven. The disk of gas swirling around the black hole may matter just as much. Picture two different kinds of disks. One is thick, hot and puffed up, almost like a donut of glowing gas. The other is thin, flat and cool, more like a dinner plate, spiraling slowly inward. Some models suggest that a thick, puffed-up disk is far better at anchoring strong magnetic fields, which may be the key ingredient for launching a jet. A thin, quiet disk might starve the same mechanism of the field strength it needs. If this is right, then whether a black hole roars or stays silent could depend less on the black hole itself and more on how its food arrives. Some of the most extreme jets ever measured came from quasars, the blazing cores of active galaxies first identified decades ago as impossibly bright points that turned out to be entire galactic centers. A handful of these jets appear to fling material outward at more than 99% of the speed of light. Nothing built by human hands has ever come close to matching that. Our best particle accelerators on Earth push protons to high energies over rings many kilometers wide. These cosmic jets do something similar across distances of thousands of light years, using only gravity, spin, and magnetic fields as their machinery. At the far end of the scale sit the radio galaxies, whose jets have inflated bubbles of hot gas stretching for millions of light years, some of the largest single structures shaped by any object in the universe. At the other end are black holes that seem to be doing everything right, feeding steadily, spinning, surrounded by hot gas, and yet producing no jet at all that we can detect. Nobody has a clean answer for why. One more wrinkle deepens the mystery. Some black holes seem to switch their jets on and off over time, roaring for a while, falling silent, then roaring again. If jets were simply a fixed property of a black hole, this flickering would not happen. Instead, it hints that the conditions for launching a jet are delicate, perhaps balanced on a knife edge between a disk that is thick enough and a spin that is fast enough, with small changes tipping the balance. One way or the other, it is tempting to imagine a clean rule waiting to be found. Some simple formula that predicts exactly which black holes will roar. Many astronomers hope such a rule exists, but every candidate explanation so far, spin, disk shape, feeding rate, magnetic field strength, seems to explain some jets and fail on others. The honest answer today is that we are still watching from a distance, cataloging the loud ones and the silent ones, and trying to find the pattern hiding underneath. For now, the roaring black holes and the silent ones sit together in the same sky, equally massive, equally real, and equally unexplained. Somewhere in that contrast may be the clue that finally reveals how these engines choose to speak or choose to stay quiet. Let's rest for a moment on something small. Not the jet itself, not the great arc of light crossing 100,000 light years. Something smaller. The spin a black hole can spin. This is one of the strange, quiet truths about them. They have no surface, no solid ground, nothing you could touch and call the black hole itself. And yet they turn, space around them turns with them, dragged along like water pulled into a slow whirlpool. Physicists call this frame dragging, and it happens because the black hole's rotation twists the fabric of space nearby, forcing anything close, even light, to move along with the spin whether it wants to or not. Some researchers wonder if this spin is the missing piece. The idea, called the Blandford's-Nyjak mechanism, after the two physicists who first worked out the mathematics, suggests that a spinning black hole can act like a kind of cosmic dynamo. Magnetic field lines get caught in the twisting of space near the black hole. As they twist, they tighten, and that tightening may be able to pull energy directly out of the black hole's rotation itself, not out of the swirling gas nearby, out of the black hole, out of pure spin. It is a strange thought to sit with. A black hole loses energy the same way a spinning top slows down when friction works against it. Except here, the friction is made of magnetic fields, threading through warped space. If this idea holds, then the jet is not just a leftover of infalling matter. It is a piece of the black hole's own rotation, carried outward, turned into light and speed and structure, spanning galaxies. But here is where the puzzle deepens rather than resolves. Astronomers have found what looks like a pattern. Black holes that spin quickly seem, in many cases, to launch stronger, faster jets. Black holes that spin slowly, or barely at all, often stay quiet. It is a tempting correlation, the kind that feels like it should be a proof. Yet nature rarely gives such clean answers. And this one comes with exceptions that resist easy explanation. Some black holes with fast spin show no jet at all. Others, spinning only modestly, launch jets that stretch far beyond their host galaxies. The link between spin and speed is real enough to notice, weak enough to argue about, and stubborn enough that no one has closed the case. Part of the difficulty is that spin is almost impossible to measure directly. There is no needle, no dial, nothing to read from a distance. Astronomers infer it indirectly, often by studying the glow of the inner accretion disk, the ring of gas and dust spiraling inward before it disappears past the event horizon, the boundary beyond which nothing, not even light, can return. The shape and behavior of that glow can hint at how close the disk sits to the black hole, and that closeness depends on spin. But every inference carries uncertainty, and every measurement leaves room for a different interpretation. There is a competing idea, gentler in some ways, that the magnetic field itself matters more than the spin underneath it. In this view, a black hole surrounded by a strong, well-ordered magnetic field might launch a jet almost regardless of how fast it turns, while A black hole with a weak or tangled field might stay dark even while spinning quickly. If this is closer to the truth, then spin is not the engine. It is only one gear among several, and the magnetic field is doing quiet work that spin alone cannot explain. What makes this section feel almost intimate, almost like peering through a microscope at the machinery of the universe, is how small the differences can be. A slightly faster spin, a slightly more ordered field, a slightly different angle where matter falls inward. These small variations may decide whether a black hole spends its life in silence or spends it firing plasma across the dark for millions of years. No one has watched a black hole spin change and watched its jet respond in real time. No one has measured with full confidence how much of a jet's power comes from spin and how much comes from the swirling disk feeding it. The relationship sits somewhere between correlation and mechanism, observed but not fully understood, promising but incomplete. It is a small mystery, living inside a much larger one, easy to overlook, easy to sleep past, but it captures something true about this whole subject. The universe often shows us a pattern before it shows us a reason. We notice the shape of the thing before we understand why the shape exists, and for now, the spin and the speed remain linked by observation alone, waiting for an explanation the universe has not yet offered us. Somewhere over Utah's high desert, a field of instruments waits in the dark for a visitor, but almost never comes. Each detector sits under the stars like a lonely metal dish, tuned to catch a whisper. Sometimes, once a week, once a month, one of them catches a flash of light so faint it barely counts as light at all. That flash comes from a single particle that has crossed the universe and slammed into the sky above the desert. Its energy can rival that of a thrown baseball, all packed into one invisible speck. This story begins in 1938, when a French physicist named Pierre Auger noticed something strange. He placed detectors far apart from each other, expecting silence between them, and instead, they clicked in unison, as if some single event had reached across a great distance and touched them all at once. Auger realized a cosmic ray, a particle from space, had struck the upper air and shattered into a wide shower of smaller particles. The shower spread out like an invisible umbrella, wide enough to trigger detectors far apart. He had found a messenger, he had not found its sender. For decades, the sender stayed hidden. Cosmic rays of ordinary strength were traced, slowly, to sources within our own galaxy, likely the aftermath of exploding stars. But some particles carried far more energy than any known stellar explosion could explain. These were the ultra-high energy cosmic rays, particles so energetic that physicists struggle to imagine what engine could fling them so hard. A supernova did not seem strong enough. Something larger was needed, something with more reach and more force. Attention turned outward, past the galaxy, toward the centers of other galaxies entirely. The idea took hold at a supermassive black hole, one that had somehow found a way to launch a jet of matter close to the speed of light, might act as a natural particle accelerator, far more powerful than anything humans could build on Earth. The jet's shock fronts, where fast plasma slams into slower gas, could in theory work like a slingshot, boosting particles again and again until they reached impossible speeds. It was a compelling idea. It was also, and remains, unproven. To test it, scientists built bigger nets. The Pierre Auger Observatory, named for the man who first noticed the showers, now spans an area of the Argentine Pampas, roughly the size of Rhode Island. It uses over 1,000 ground detectors, and on clear moonless nights, ultraviolet telescopes that watch the sky glow as a shower rains down through the air. Every detected event gets logged. its arrival direction traced backward, like a detective following footprints in reverse. The hope was simple. If enough events point back to the same patch of sky, that patch should hold the source. The results have been suggestive rather than certain. Some of the highest energy events cluster loosely near active galaxies, the ones known to host black holes launching jets. But magnetic fields fill the space between here and there, invisible currents that bend a charged particle's path many times over its long journey. A particle that seems to come from one direction might have started somewhere else entirely, its true path scrambled by fields we cannot fully map. This bending is one of the deepest frustrations in the search. It means cosmic rays, unlike light, cannot simply be traced back to a single point with confidence. Some researchers wonder if a mix of sources is responsible, with distant blazars, the jets aimed straight at Earth, contributing some particles while other galactic engines contribute the rest. Others wonder if the accelerating shocks lie farther out in a jet structure than once assumed, in the giant lobes, where a jet finally slows and spreads after slamming into the space between galaxies for 1 million years or more. Neither idea has been confirmed. Neither has been ruled out. What the decades of hunting have shown is a pattern of near misses. Each new observatory, each larger array of detectors, has sharpened the picture just enough to rule out simple answers, without delivering a clear final one. The particles keep arriving, faint and rare, carrying energy from some source that remains, even now, only partly understood. Whatever black hole engine sent them left no return address, only a trail bent and scattered by every magnetic field it crossed on the way. The desert waits. The instruments wait with it, patient in the dark, still listening for the next quiet flash that might, someday, finally point the way home. Day. Jet does not travel forever. At some point, after crossing thousands of light years of near-perfect emptiness, it runs into something. And what happens next still puzzles the people who study it. Picture a beam of plasma moving at nearly the speed of light, plunging into the thin gas that drifts between galaxies. This gas is not much. A few atoms per cubic meter, spread so thin it would count as a vacuum in almost any lab on Earth. And yet, the jet slows down. It pushes against this whisper of matter, the way a fast river pushes against still water. And something has to give. What gives is the jet itself. It does not stop cleanly. It flares outward into a glowing structure called a radiolobe, a great soft cloud of particles and magnetic field that can spread wider than the galaxy that made it. These lobes shine brightly in radio waves, though they are almost invisible in ordinary light. For decades, astronomers saw these glowing shapes in the sky before they understood where they came from, or that a small black hole at the center of a distant galaxy was somehow responsible for something so vast. Here is the part that still seems strange, even to people who study it for a living. The jet does not fade away gradually, the way a stream of water might spread and slow. Instead, it often ends in a bright knot, a place where the fast-moving particles seem to crash into a kind of wall. This bright spot is called a hot spot, and it marks where the jet's motion suddenly turns into heat and light. Some researchers compare it to the tip of a fast stream of water hitting a pool. Others are not sure the comparison holds, because the physics of plasma moving near the speed of light does not always behave the way water does. One open question is why the jet stays so narrow for so long before this collision happens. A beam of gas should spread out as it travels, the same way smoke spreads from a chimney, that these jets often stay tight and focused across tens of thousands of light years, almost like a beam of light from a very distant, very patient flashlight. Some scientists think magnetic fields hold the jet together, wrapping around it like an invisible sleeve. Others wonder if something about the surrounding gas itself acts as a kind of channel, guiding the jet the way a riverbed guides water. Neither idea fully explains what has been observed. There is another surprise hiding in these collisions. When a jet slams into the gas around it, it does not just make light. It can also stir up the gas across an entire cluster of galaxies, gently heating it and slowing down the collapse of that gas into new stars. Some researchers think this may explain why certain giant galaxies stopped forming stars long ago, as if the jet acts like a slow, invisible thermostat. But other galaxies with similar jets do not seem to show this effect as clearly, and no one is certain why the pattern is so uneven. Sometimes the meeting between jet and empty space produces something even less expected. A few jets appear to bend, as though something invisible nudged them sideways after they had already traveled a great distance. One idea is that the black hole itself wobbles slowly over long stretches of time, tilting the jet's launch angle bit by bit. Another idea is that the jet is moving through a lumpy, uneven bath of gas and simply follows the path of least resistance, like a stream finding gaps between rocks. Both ideas are reasonable, neither has been confirmed. What makes all of this quietly remarkable is the contrast in scale. The jet begins in a region smaller than our solar system, shaped by forces near the edge of a black hole. It ends, sometimes hundreds of thousands of years later, in its own timeline, spreading into a glowing lobe wider than the galaxy that gave it birth. Somewhere in between, matter that once orbited a black hole slams into the thin gas of the space between galaxies and turns into light we can still detect today. We are left with a jet that begins in extreme gravity and ends in near emptiness, carrying its story across a distance the mind can barely hold. The middle of that story, the long quiet stretch where the jet stays narrow and travels almost untouched, remains only partly understood. It is a reminder that even after decades of watching these beams cross the sky, the universe still keeps some of its simplest questions to itself. Rest here a moment, and let your mind drift towards something almost impossible to picture. Somewhere near the center of a distant galaxy, a black hole sits inside a ring of glowing gas. Around it, a jet begins. The place where that jet is born is smaller than our solar system, and yet the light from it has crossed billions of light years to reach a telescope on Earth. To see that tiny point clearly, astronomers needed something more than one dish pointed at the sky. They needed to link dishes together across entire continents, so the whole Earth became one enormous eye. This method has a simple name and a complicated result. It is called Very Long Baseline Interferometry. Signals from radio telescopes in different countries, sometimes different hemispheres, are combined with exquisite timing so that the small differences between them reveal detail no single telescope could ever capture alone. The wider the spread of telescopes, the sharper the final image becomes. When astronomers linked dishes from Hawaii to Spain to Chile to the South Pole, they built something with the resolving power of a telescope the size of the planet itself. This effort produced the first image of a black hole's shadow, a dark circle ringed by glowing plasma, bent and pulled by gravity so strong that light itself curves around it. The image was faint, blurry by ordinary photograph standards, more like a soft orange ring than a crisp photograph. But it was real. It showed, for the first time, the edge of the region where a jet is thought to begin. Even so, the shadow only shows us the outer boundary. What happens at the very base of the jet, in the last few miles before matter either falls in or escapes, remains hidden from direct view. This is where the wider symphony of the universe becomes useful. A jet does not act alone. It reaches out and touches the gas around it, the dust between stars, sometimes the space between entire galaxies. Watching how that surrounding material responds gives astronomers a second way to study the jet's engine, even without seeing the engine itself. It is a little like understanding a waterfall by watching the ripples it sends across a lake, long after the water has left the ledge. Some researchers compare this to how the sun's activity ripples outward to shape the delicate tides of Earth's oceans and the shimmer of the northern lights. Nothing about a black hole jet works quite the same way, but the pattern of influence rhyming across distance feels familiar. Small, energetic source at the center sends its effects outward in ways that touch systems far larger than itself. The sun is many times smaller than the solar system it governs. A black hole is smaller still compared to the galaxy that feels its jet. One open question is whether the shadow images taken so far of only 2 black holes tell us anything general about how all jets begin. Perhaps the mechanism looks the same everywhere, just scaled by mass and spin, or perhaps each black hole's surroundings, its magnetic field, its supply of gas, shape the process differently every time. The evidence so far is thin, drawn from a small handful of systems. Broader patterns remain guesses dressed as theories. There is also the harder question of resolution. Even a telescope the size of Earth cannot see everything. The jet's true launch point, right at the boundary between the accretion disk and the event horizon, may still be too small and too fast-changing for any Earth-based instrument to resolve clearly. Some scientists hope that future arrays, perhaps even telescopes placed in space to widen the baseline further, could sharpen the picture. Others wonder whether some part of this process will always stay just past the edge of what we can observe, no matter how clever the instrument. For now, the shadow images stand as a rare kind of proof, not a full explanation, but a confirmation that the invisible edge is real, and that our instruments can, in a limited way, reach toward it. The jet's true birthplace remains a place we infer more than we see. We watch its shadow, we watch its ripples spreading through galaxies. We build careful models from the traces it leaves behind. Whether that adds up to true understanding, or only a very detailed sketch of something still beyond our grasp, is a question every astronomer studying these systems must sit with quietly, the same way you might sit with the thought of it now, in the dark, waiting for sleep. Most black holes that launch jets do not launch just one. They launch 2. Picture a spinning top with a beam of light shooting from its north pole and another beam shooting from its south pole. That is roughly the shape of a jet system. 2 beams pointed in exactly opposite directions, both moving at nearly the speed of light. This makes a kind of sense. If a jet forms along the spin axis of a black hole, then space itself gives you 2 ends to that axis. Whatever process launches material outward on one side should, in theory, launch matter outward on the other side too. The universe, in this picture, seems to prefer balance. 2 beams, mirror images of each other, racing away into the dark in equal and opposite directions. But when astronomers actually look at these systems, the 2 beams often do not look equal at all. In many jets, one beam appears bright and clearly visible, stretching far out into space. The other beam, the one pointed in the opposite direction, is often faint. Sometimes it is barely visible. Sometimes it seems to vanish almost completely, as though only one half of the pair survived the journey. For a long time, this puzzled observers. If the launching mechanism is symmetric, why would the result look so lopsided? One explanation involves something called relativistic beaming, a strange effect that happens when material moves close to the speed of light. Light from a jet moving toward Earth gets concentrated and brightened, almost like a flashlight beam pointed straight at your eyes. Light from the opposite jet, moving away from Earth, gets stretched out and dimmed, like a flashlight pointed away from you into an empty room. The two jets might be launched with equal strength. What we see may simply depend on which way they happen to be tilted relative to our little vantage point on Earth. This idea explains a great deal. It accounts for why some jets, called Blazars, appear almost impossibly bright, while their hidden twin on the far side stays dark and quiet in our sky. It suggests that the true symmetry might be real, even when the picture we receive is not. Yet this explanation, while widely supported, does not answer every case. Some jets show real physical differences between their two sides, differences that seem too large to be explained by viewing angle alone. In a few systems, one jet appears to plow into a denser pocket of gas, slowing down and lighting up in ways its twin, moving through emptier space, never does. In others, the surrounding galaxy itself may be lopsided, offering one jet a clearer path and choking the other with debris. So the asymmetry we see may come from several overlapping causes: the geometry of our view, the terrain each jet happens to cross, and possibly something happening even closer to the black hole itself, something we still cannot see directly. That last possibility keeps some researchers awake with curiosity. If the launching engine near the event horizon is not perfectly stable, the two jets might not start out equal at all. Slight wobble in the black hole's spin, a brief imbalance in the magnetic field threading through the disk, and one beam could begin its life already weaker than its twin. Over centuries, that small difference could grow, the way a single stumble at the start of a long walk changes the whole path that follows. There is something quietly moving in this question of symmetry. It touches on a larger pattern seen across the universe, the tendency for grand, violent processes to still carry some trace of order within them. Spinning stars, spinning galaxies, spinning black holes, each one finding some way to balance its energy outward in more than one direction. And yet nothing in nature seems to insist on perfect balance forever. Small asymmetries creep in, environments differ, one side finds an easier road than the other. Astronomers continue to study jet pairs across many galaxies, comparing their brightness, their length, their angle to Earth, hoping to separate what is caused by our viewing position from what is caused by real physical difference near the source. The instruments keep improving. The catalogue of known jet systems keeps growing, but the deeper question, whether every jet truly begins as a matched pair and simply appears otherwise, or whether true asymmetry can be built into the launching process from the very first moment, remains open. For now, we are left watching two beams of light, born from the same dark engine, journeying outward into the void, and wondering whether they were ever really the same to begin with. Picture a coil of wire glowing faintly, twisted into loops that pull tighter and tighter near a black hole. That image is close to what some scientists believe is happening, though no one has ever seen it directly. Magnetic fields near a spinning black hole may act like invisible slingshots, catching charged particles and throwing them outward at speeds close to light itself. The light we see from these jets is not the black hole itself. It is the story of what the magnetic field is doing to matter, caught in its grip. Close to the black hole, gas swirls in a thin, hot disk. Friction inside that disk heats the gas until it glows, and that glow spans colors far beyond what our eyes could ever register, from soft radio waves to searing X-rays. But the jet itself, the long thread of matter shooting outward, often glows in a very different way. It shines through something called synchrotron radiation, a kind of light made when charged particles spiral around magnetic field lines at nearly the speed of light. This light carries a signature. It often looks slightly polarized, meaning the light waves line up in a preferred direction, like sunlight glinting off a lake at a certain angle. That polarization is one of the few clues we have about the hidden magnetic architecture inside a jet. When astronomers measure it, they are essentially reading the alignment of magnetic field lines millions of light years away. Some jets show tightly organized, almost braided patterns, as if the magnetic field were wound like a spring. Other jets show tangled, chaotic polarization, suggesting a much messier structure. Nobody fully agrees on why some jets look ordered and others look scrambled. One idea is that a strong, stable magnetic field near the black hole produces a neat spiral structure that holds together for enormous distances. A competing idea suggests that turbulence within the disk constantly reshapes the field. So the order we sometimes see is temporary, a passing calm in something inherently unstable. The colors of these jets, if we could somehow shift them into visible light, would likely surprise us. Much of the emission sits outside what human eyes can perceive, glowing instead in radio and X-ray wavelengths. Yet if we imagine translating that invisible light into something we could see, the base of a jet might appear as a tight, blue-white knot, hot and violent, fading outward into softer red and orange hues as the particles lose energy over vast distances. Some parts of a jet even brighten suddenly, flaring for reasons that remain unclear. One hypothesis suggests that these flares happen when the magnetic field lines snap and reconnect, releasing bursts of energy, much like a rubber band suddenly let go. Another possibility points to shocks forming when faster material rushing outward slams into slower material ahead of it, compressing the field and igniting a brief, brilliant glow. The color and brightness of these shocks might also depend on what the jet is actually made of, and that remains one of the open questions in this field. If the jet carries mostly electrons and positrons, the light it produces would follow one kind of pattern. If protons carry a significant share of the energy, the emission might behave differently, since protons radiate less efficiently than lighter particles. Some researchers argue that jets must contain protons to explain their sheer power, since electrons alone might not carry enough punch across such distances. Others argue that pure electron-positron jets can still work, if the magnetic field does most of the heavy lifting instead of the particles themselves. The light we observe cannot yet settle the argument. At larger scales, when a jet finally slows and spreads into vast lobes of glowing plasma, the light softens into a diffuse haze, sometimes stretching wider than the galaxy that made it. These lobes glow faintly for millions of years, like the last light behind a curtain after the source has gone quiet. Their color, mostly hidden from human sight, tells us how the particles have cooled, how the magnetic field has relaxed, and how far the energy has traveled from its origin. None of this light tells us exactly how the slingshot begins. We can trace it, model it, and admire its glow from thousands of light years away. But the innermost mechanism, the precise twisting of space and magnetism near the event horizon, stays hidden behind distance and physics we do not fully understand. Color of the jet is a message sent across unimaginable space. What remains uncertain is whether we are reading that message correctly or only catching the parts bright enough to reach us at all. Space carries no sound the way air does. There is no medium to carry a wave into your ear, no atmosphere to shake with a rumble. And yet, in a strange and quiet way, some of these jets do produce something we can almost call a hum deep in the Perseus cluster, a group of thousands of galaxies bound together by gravity. Astronomers found ripples moving through the hot gas between the galaxies. Those ripples came from a black hole jet, pushing outward again and again over millions of years. When researchers translated the pattern into sound, raising it many octaves so human ears could register it, they found something close to a single, steady note. It has been described as a B-flat, sounded 57 octaves below the middle of a piano. It is not something you could ever hear with your own ears, floating in space, but it is a real pressure wave, moving through gas so thin it barely counts as matter, spreading out from the black hole like a slow, endless breath. That detail matters for the mystery, because it shows that a jet is not just a beam of light and particles racing away in a straight line. It also pushes on its surroundings. It compresses gas, stirs currents, and sends waves rolling outward, the way a stone sends ripples across a still pond. Except this pond is a cluster of galaxies, and the ripples take millions of years to cross it. Some researchers think these slow waves may be one part of the answer to a long-standing puzzle called the cooling flow problem. Hot gas at the center of galaxy clusters should cool and fall inward, forming huge numbers of new stars. But it mostly does not. Something keeps stirring the pot, keeping the gas warm and turbulent. A jet, breathing outward in one long, low tone, might be doing exactly that job. Other researchers are not convinced the sound wave itself carries enough energy, and instead point to the hot bubbles the jet blows into the gas, which slowly rise and mix like thermals over a summer field. Both ideas may be part of the picture. Neither is fully confirmed. There is a second kind of sound worth sitting with, one that comes from a very different corner of the mystery. Radio telescopes do not hear jets, not in the way your ears hear a whisper, but they detect radio waves, a form of light far beyond what our eyes can see. And those waves can be converted into audio, the same way sunlight can be turned into the click of a Geiger counter. When astronomers do this with data from jets and their radio lobes, the vast structures they blow into space that can stretch across 1 million light years, they often get static, hiss, and crackle. It sounds almost like static on an old radio, restless and uneven. Some listen to it and hear chaos. Others hear a kind of texture, evidence of turbulence inside the jet itself, of magnetic fields twisting and snapping as particles race through them at nearly the speed of light. What is genuinely unresolved is how much of that inner texture we are actually capturing. A jet begins somewhere very close to the black hole, in a region so small and so violent that no telescope has ever imaged it directly. By the time the signal reaches us, it has already traveled thousands, sometimes millions, of light years. The sound we make from that signal is a kind of echo of an echo, shaped as much by the space it passed through as by the engine that made it. Whether the hiss we hear reflects turbulence born right at the black hole, or turbulence added much later by the jet's slow collision with surrounding gas, is still an open question. Different regions of a single jet may even carry different answers. There is something quietly moving about a jet that hums for millions of years, low and steady, long after the star systems near it have changed and drifted. The black hole that started it may have gone quiet by the time the wave finally fades. The galaxies it passes through may never know the wave is there. It moves through them anyway, patient and enormous, doing work we are still trying to fully understand. No one standing in that gas would feel a sound. But if you could slow down time and speed up your hearing by unimaginable amounts, you might catch that one long low note drifting outward from a black hole that decided once to breathe. Picture a black hole not as a single roaring engine, but as something that switches on and off, sometimes over centuries, sometimes over millions of years. This is one of the quieter puzzles in the story of cosmic jets. The math that describes this rhythm is simple to write down, living inside that math. For now is a question nobody has fully answered. The basic ratio is easy to picture. A black hole needs fuel to launch a jet. That fuel is gas and dust, spiraling inward through the disk we spoke of earlier when the supply is rich. The disk glows bright, and the jet, if one forms, can be powerful and steady. When the supply thins out, the disk grows faint, and the jet may weaken or stop entirely. Astronomers describe this with something called the accretion rate, a simple measure of how much mass falls toward the black hole each year. It sounds small and technical, but small changes in that number seem to produce enormous changes in what shoots out the other end. Here is where the beauty and the mystery sit together. Some black holes seem to need only a trickle of gas to keep a jet running for a very long time. Others, fed at similar rates, stay dark and silent. The ratio between fuel in and energy out does not behave the same way from one black hole to the next. One idea holds that the spin of the black hole changes this ratio, so a fast-spinning giant can turn a thin trickle into a bright jet, while a slow-spinning one cannot. A competing idea points instead to the magnetic field threading the disk, suggesting that field strength, not spin, decides who gets an engine and who does not. Both ideas rely on elegant numbers. Neither has been confirmed as the full answer. The timing of these on and off cycles adds another layer. Radio observations of some galaxies show jets that seem to have shut off, leaving behind ghostly lobes of plasma still drifting outward, slowly cooling, long after the central engine went quiet. Other galaxies show fresh, narrow jets pushing out from a black hole that looks, by every other measure, calm. Somewhere in between are galaxies with two sets of lobes, an old faded pair and a new bright pair, like rings in a tree trunk. Each pair marks a separate outburst, sometimes separated by tens of millions of years. The rhythm of feeding and starving appears to repeat, but the length of each phase does not follow one single, tidy formula. There is something almost musical about this switching. A jet might run for 100,000 years, then fall silent for 1,000,000, then wake again when a fresh cloud of gas, maybe from a passing dwarf galaxy, or a slow gravitational nudge, spirals close enough to feed the disk once more. The numbers involved span such enormous stretches of time that no human observation could ever watch a full cycle unfold. Instead, astronomers piece the story together the way a geologist reads rock layers, using faint lobes and diffuse plasma trails as evidence of a past that no one saw happen. One of the open questions inside this rhythm involves galaxy clusters, the huge collections of galaxies bound together by gravity, swimming in hot gas that should, by simple physics, cool and collapse into new stars. It mostly does not. Something keeps reheating that gas, and jets from central black holes are the leading suspect, switching on just often enough to stir the pot and slow the cooling. If this is correct, the on and off nature of jets is not just a curiosity. It may be one of the quiet mechanisms holding an entire cluster of galaxies in balance, feeding heat back into gas that would otherwise settle into stars. But the exact trigger for each switch remains unclear. Is it a change in gas supply alone? Is it a shift in the magnetic field wrapped around the disk? Is it some change deep near the event horizon? The boundary we still cannot see clearly. Different galaxies seem to answer differently, and that alone tells us something important. There may not be one single rule for how a black hole starts and stops its jet. There may be several rules, tangled together, expressed through slightly different numbers in every case. What remains genuinely open is whether this rhythm follows any predictable pattern at all, or whether it is closer to a slow cosmic flicker, shaped by chance encounters and passing clouds of gas. The ratios are elegant on paper. The behavior they produce, out among the stars, still resists a single tidy explanation. For now, the switching continues, unseen, unmeasured, in real time, somewhere above us in the dark. Somewhere in the dark, two galaxies drift toward each other. This has happened many times before. Across the long history of the universe, each galaxy carries a supermassive black hole at its center, quiet or roaring, spinning at its own private speed. When the galaxies finally merge, their black holes may spiral together too, circling closer over millions of years, until they meet in an event we still struggle to imagine. What happens to a jet, an accelerator built from spinning space and magnetic field, when its source is about to collide with another black hole entirely? This is one of the more delicate questions in the study of these engines. A jet depends on a careful balance. It needs a spinning black hole, a disk of gas feeding it at the right rate, and a magnetic field threaded through both. Twisted just so, change any one piece, and the jet can falter. A merger changes all three at once. Some researchers wonder whether the final stages of a black hole merger could briefly create the most powerful accelerator the universe has ever produced. As two black holes spiral together, tidal forces can heat and compress any surrounding gas into extreme state, hotter and denser than anything in a stable disk. If a magnetic field is present and organized in the right way, this violent moment might, in theory, drive a jet far more energetic than the slow, steady jets we see in most active galaxies today. It would be a brief burst, not a lasting stream, but a burst of almost unthinkable power. Other researchers are more cautious. A merging black hole system is chaotic. Space itself ripples and twists as gravitational waves carry energy away. Magnetic fields, delicate structures at the best of times, may simply not survive that kind of disruption. A field that gets tangled and torn apart cannot organize itself into the neat, spiraling shape a jet seems to need. In this view, mergers might be too rough an environment for jets, not too powerful an environment for them. The truth may depend on timing. Before the final plunge, while the black holes still orbit at a comfortable distance, conditions might resemble an ordinary feeding black hole, calm enough to sustain a jet. In the last moments before merger, though, the black holes move at speeds close to the speed of light itself, and the fabric of space around them churns with a violence that has no equivalent anywhere else in nature. Whether a jet could survive that final plunge, or whether it would be born from it, remains genuinely unknown. There is a reason this question matters beyond curiosity. Every accelerator we have studied so far exists because of a fragile arrangement: spin, feeding rate, and magnetic geometry, all lined up in a way that seems almost improbable when you consider how many things could go wrong. A black hole spinning too slowly may not have enough energy to extract a disk. Feeding too quickly can smother a jet before it forms. A magnetic field too weak or shaped wrong may fail to grip the spinning space at all. The jets we see are not the rule. They may be closer to an exception, a narrow window where all the pieces happen to fit. A merger tests every one of these conditions simultaneously. The final spin of the combined black hole depends on the masses and spins of the two originals, and on the geometry of their inspiral, in ways astronomers can model, but not yet observe directly. Some mergers might leave behind a black hole, spinning faster than either original, primed for a jet. Others might leave a black hole, spinning more slowly, less capable of launching one. The magnetic field, if it survives, adds another layer of uncertainty on top of an already uncertain calculation. Gravitational wave observatories have begun to detect black hole mergers directly. Sensing the ripples in space, these collisions send outward. So far, most confirmed mergers involve black holes far smaller than the supermassive kind that power galactic jets. Whether the same physics scales up to the giant mergers expected when galaxies collide is still an open question, one that may only be answered as detectors sensitive to lower frequencies come into use in the coming decades. For now, the picture stays incomplete. A jet is already a delicate thing, a needle-thin stream of near-light-speed plasma balanced on the edge of a black hole's spin. A merger is one of the most violent events the universe can produce. Whether these two fragile, extreme processes could combine into something even more powerful, or whether one would simply destroy the conditions the other needs, is a question no one has fully answered. Somewhere out there, perhaps, two black holes are spiraling together right now, and we do not yet know what kind of light, if any, that final embrace might send across the dark. Far from any black hole, deep under the ice of Antarctica, sits one of the strangest telescopes ever built. It has no lens, it has no mirror. It is made of light sensors, frozen into a cubic kilometer of ancient ice, waiting for something almost too small to imagine. That something is a neutrino, a tiny particle with almost no mass and no electric charge, so shy that it can pass through an entire planet without touching a single atom. Neutrinos are sometimes called ghost particles. They slip through walls, through mountains, through the whole Earth, unnoticed, and yet, once in a great while, one of them strikes a molecule of ice deep in that Antarctic array, and a faint blue flash of light gives it away. When that happens, scientists ask a quiet question: where did this particle come from? Some of these high-energy neutrinos seem to arrive from very specific points in the sky, and a few of those points line up with Blazars, those black hole jets that happen to point straight at Earth. One event in particular, detected in 2017, seemed to trace back to a blazar billions of light years away. It was one of the first times a single neutrino had been connected, with reasonable confidence, to a specific cosmic source. This matters because neutrinos are not easy to make. To produce one at these energies, something has to accelerate a proton to tremendous speed, and then that proton has to collide with something else, light or matter, in a way that creates a neutrino as a byproduct. Jets from supermassive black holes are one of the few places in the universe violent enough and large enough to do this again and again. If jets are making neutrinos, that would help answer a question raised earlier in this story. It would tell us that jets carry protons, not just lighter particles like electrons, and that those protons are being flung out at nearly the speed of light. But the evidence remains thin. One neutrino, traced to one blazar, is a beginning, not a proof. Some researchers wonder whether it was a coincidence, a chance alignment between a rare particle and a bright source that happened to be flaring at the right moment. Other detections since then have added support, but the numbers are still small. Ghost particles do not arrive often, and when they do, tracing their path back across billions of light years carries real uncertainty. The sky is wide, and blazars are not the only bright things in it. There is also the deeper puzzle of where, exactly, Inside a jet, these neutrinos might form. Some models place the collisions close to the black hole, in the crowded, energetic region near where the jet is born. Other models suggest the neutrinos form much farther out, in shocks that develop as the jet plows into gas far from its source, the same kind of shocks that create the giant radio lobes described earlier. These two pictures would mean very different things about how jets are built and where their power is concentrated. Right now, the data cannot fully separate one idea from the other. What makes this pursuit so quietly thrilling is what a neutrino represents. Unlike light, which can be bent, absorbed, or scattered on its way to us, a neutrino travels in an almost perfectly straight line. It ignores magnetic fields. It ignores clouds of dust. If astronomers can catch enough of them and trace their origins with confidence, neutrinos could become a kind of direct messenger from the heart of a jet, carrying information that no photon ever could. It would be a little like receiving a letter that had passed through solid stone without smudging a single word. That kind of messenger has not fully arrived yet. The detectors are getting better. New arrays are being planned, some to be built in ice, others in the deep sea, each one hoping to catch more of these fleeting flashes and build a clearer map of where they come from. For now, the connection between black hole jets and cosmic neutrinos remains a promising thread, pulled but not yet unraveled. It is a strange comfort, in a way, to know that somewhere above you tonight, ghost particles are raining down, most passing through you without a trace, one or two carrying a story from a black hole billions of light years away. We do not yet know how many of those stories start in a jet. We do not know if every blazar makes them, or only some, under conditions we have not identified. The question sits quietly in the dark, waiting for more data, more ice, more patient nights of watching. For now, it remains one of the sky's most delicate, open threads. Somewhere in a laboratory on Earth, a machine called a particle accelerator pushes protons close to the speed of light. That machine spans miles. It took thousands of people to build it. And yet the jets we have been describing tonight make that human effort look small, a black hole with no moving parts, using only gravity and magnetic fields, can outperform our best engineering by many orders of magnitude. This gap between what nature does casually and what we can barely do with great effort is part of why these jets sit at the edge of physics. Physicists who study particles on Earth and physicists who study jets in space have started talking to each other more. This is a fairly new development. For a long time, these were separate fields, each with its own instruments and its own language. Now there is a shared curiosity. Could the extreme conditions inside a jet teach us something about particle physics that no machine on Earth could ever show us? Some researchers think yes. The energies inside a jet may be so much higher than anything achievable in a laboratory that new physics, rules we have not yet written down, might only reveal itself out there. One open question is whether the particles in these jets ever reach energies where our current understanding of physics starts to break down. We have equations that describe how particles behave at the energies we can test on Earth. Those equations work very well here. But a jet from a supermassive black hole might push particles into territory where those equations have never been checked against real data. Nobody knows for certain what happens in that territory. It may be that our physics holds up perfectly, extending smoothly into realms we cannot yet reach in a lab, or it may be that something new is waiting there, some detail our best theories have missed. The event horizon itself remains part of the mystery. That is the invisible boundary around a black hole, beyond which nothing, not even light, can escape. We still do not have a direct, sharp image of what happens right at the base of a jet, in the region closest to that boundary. Our best images, remarkable as they are, blur that innermost zone into a soft glow. Future instruments, perhaps arrays of telescopes spread even farther across the Earth, or even telescopes placed in space, might someday resolve that region more clearly. If they do, we may finally see the handoff, the exact place where swirling matter and twisted magnetic field lines turn into a beam of light-speed particles. Until then, that handoff remains theoretical, built from equations rather than direct sight. There is also the question of what these jets can tell us about gravity itself. Einstein's theory of general relativity, our best description of gravity, predicts how space and time should bend near a spinning black hole. Jets may be one of the few natural laboratories extreme enough to test that theory in conditions we cannot recreate any other way. So far, the observations we have made fit the predictions reasonably well, but the fit is not perfect in every detail, and some researchers wonder if tiny discrepancies, so far explained as measurement limits, might eventually point towards something gravity itself does that we have not yet accounted for. Others expect the theory to hold exactly as it has held under every previous test. None of this is settled. That is worth sitting with for a moment, quietly, in the dark. The universe is not offering us tidy answers tonight. It is offering us a genuinely open frontier, one where a slow, careful search for better instruments and better ideas might, over years or decades, reveal something we cannot yet imagine, or it might simply confirm what we already suspect, filling in details rather than overturning them. Both outcomes would be valuable. Both outcomes would still leave new mysteries behind, because that is how this kind of searching tends to work. Long after our instruments improve, long after new telescopes are built and old questions are answered, the black holes themselves will keep doing what they do. They will keep pulling matter inward. They will keep twisting magnetic fields into invisible funnels. They will keep launching threads of light-speed particles across the dark, indifferent to whether anyone is watching or measuring. The edge of physics, wherever it truly lies, is not a fixed line. It moves as our tools improve, retreating into the distance like a horizon that keeps stepping back as we walk toward it. For now, we watch from far away, gathering faint light, and wonder how much of the story we are only beginning to read. Some of the oldest light we can see comes from jets that lit up when the universe was very young. Astronomers have found quasars whose light left home when the cosmos was less than 1 billion years old. That light has been traveling for over 13 billion years to reach our eyes tonight. When we look at these ancient jets, we are not just looking far away, we are looking back in time, to an era before most galaxies had even finished forming. This raises a quiet, humbling question. How did black holes grow massive enough, fast enough, to launch jets so early? Some of these ancient quasars seem to hold black holes billions of times heavier than our Sun. The universe had barely had time to cool and gather itself into stars and galaxies. Yet, somehow, a dark engine had already formed, and had already learned how to fling matter outward at nearly the speed of light. Nobody fully knows how that happened so quickly. One idea is that the first black holes formed from the collapse of enormous clouds of primordial gas, skipping the slower step of building up through countless smaller stars. Another idea is that early black holes merged again and again, each collision adding mass and spin. Both ideas remain open, tested against the earliest quasars we can find. Each new discovery of an older, more massive black hole pushes the puzzle further back, closer to the beginning of everything. These ancient jets may have done more than move matter. Some researchers wonder if they helped shape the large-scale structure of the universe itself. A jet, stretching for 100,000 light-years, can push gas away from a young galaxy, or heat it until it cannot easily cool and collapse into new stars. If this happened often enough, in enough galaxies, jets may have helped decide where galaxies grew large and where they stayed small. This is still a hypothesis. The full story of how jets shaped the first galaxies is not yet written. There is a strange comfort in remembering that we are made of the same material as these ancient, violent engines. The iron in your blood and the calcium in your bones were forged inside stars that lived and died long ago. Some of those stars may have formed in gas clouds that were touched, heated, or scattered by a black hole's jet. We cannot trace the exact path, but the atoms in your body took a long road through the universe before they became you. And jets may have been quiet participants in shaping that road. Looking at the oldest jets also means confronting how much remains unknown about the universe's early chapters. We see the light, we measure its age and its brightness, but the moment of a jet's birth, the instant when spinning space and tangled magnetic fields first flung plasma outward near a newborn black hole, stays hidden from direct view. Even our best telescopes give us the aftermath, not the origin. The question of how the first jets were born in a universe so young remains open. Some astronomers hope that future observations, reaching even further back in time, will show us black holes just as they begin this process. Others wonder if the very first jets look different from the ones we study today, shaped by a universe with different gas densities, different chemistry, less structure to push against. If true, the jets we see nearby might be echoes of a process that has quietly changed over billions of years. If not true, the mechanism may have been remarkably stable since the universe was in its infancy. Either way, we are left with a mystery that spans nearly the whole history of everything. There is something quieting about holding this thought before sleep somewhere. Right now, ancient light from a jet older than our galaxy is still arriving on Earth, carrying a memory of a much younger universe. We did not make that light. We simply happened to be standing here, billions of years later, in its path. The particles that jet flung outward may have mixed into gas that eventually formed stars, and one of those stars may have contributed the elements that became part of you. We cannot know for certain, but the possibility is enough to make the sky feel a little less distant and a little more like home. For now, the oldest jets remain lit against the dark, their origins still unexplained, their light still arriving. That is enough to carry with you into rest tonight. We have come a long way tonight, out past the edge of what any telescope can fully show us. We have followed threads of light, stretched thin across 1,000,000 light years. We have watched, in our minds, as dark centers of galaxies reached out with invisible hands and threw streams of matter into the void at nearly the speed of light. And still, after all of that, the deepest question waits quietly where we left it. How does a black hole, a place where light itself cannot escape, manage to launch anything at all? No one has answered that question yet. Not fully. There are ideas, careful and patient ones, built from decades of watching the sky. There is the thought that spinning space itself might lend some of its motion to the particles nearby. There is the thought that magnetic fields, wound tight around a spinning giant, might act like a slingshot no human hand could ever build. Both ideas hold pieces of the puzzle. Neither one holds all of it, and that is all right. Some questions are allowed to stay open. Some mysteries are better held gently than solved too quickly. Picture, if you can, one of these distant jets right now. Somewhere out past counting, a beam of light and matter is still moving, still stretching farther into the dark. It began before our sun had planets. It may still be traveling long after we are gone. It does not need us to understand it in order to keep going. It simply moves, quiet and enormous, through a universe that has all the time it needs. And now let that image grow smaller, and smaller still, the way a candle looks smaller the farther you walk from it. Let the jet become a thin line of light far away. Let the galaxy around it become a soft, glowing disk, turning so slowly that a human life is too short to see it move at all. Let that galaxy become one point of light among billions of others, scattered across a dark so deep it has no edge we have ever found. Somewhere in all of that vastness is a much smaller, much quieter thing, a blue and white planet, turning gently in the dark, wrapped in thin air and slow clouds. Oceans move across its surface under moonlight, rising and falling the way breath rises and falls in a sleeping body. Nothing on that planet is in a hurry tonight. The tide does not rush. The night does not press. It simply continues the way it has continued for a very long time, and the way it will continue long after tonight is over. You are there, somewhere on that turning planet, lying still in a dark room. And here is a strange, comforting thought to carry into sleep. The same physics that shapes a black hole's jet, the pull of gravity, the shape of magnetic fields, the quiet architecture of space itself, is the same physics holding you gently against your bed right now. You are made of atoms that were forged inside stars long before this planet existed. In a small, real way, you are already part of the same story as those distant, roaring engines of light. You do not have to understand every part of that story to belong to it. We may learn more about these jets in the years ahead. Some future telescope, some clearer image may show us a launch point we have only guessed at so far, or the answer may stay just out of reach a little longer, waiting the way it has waited for billions of years already. Either way, the universe is not asking you to solve it tonight. It is only asking you to rest, so let the questions settle now, the way dust settles slowly through still air. Let the black holes keep their secrets a little longer. Let the jets keep moving through the dark, unwatched, unhurried, patient in a way nothing on earth ever needs to be. And let yourself do the same. Let your breathing slow. Let your shoulders soften into whatever is holding you right now. Somewhere above you, whether you can see it or not, the sky is still full of these quiet mysteries, turning gently, asking nothing of you at all. You are small beneath that sky and held by it, and that is enough. Rest now. Let the universe keep its secrets a while longer, and let sleep carry you gently into the dark. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.